give you a few more examples of working with the sum and difference identities today. We'll do a brief overview of what they are, a couple examples of things you maybe are already familiar with, and then talk about some of the challenges you're going to face as you do this problem. So these sum and difference identities are important because they relate angles that we know exact values for to new angles. And that expands our knowledge. It allows us to simplify and work with other situations. So briefly, I just want to review what these were. Recall there were 4 of them that we introduced in class. There was the sum identity for sine, which relates the sine of a particular angle to the sine and cosine of the pieces of that angle. So for example, the sine of x plus y, we found that identity was sine of x cosine y plus cosine x sine of y. We had a difference identity for sine as well. If we can express an angle in terms of the difference of 2 angles, we can come up with the identity for that as well. Sine of x minus y being sine of x cosine of y minus cosine x sine of y. We also had 2 identities for cosine. Just to review those briefly, we'll put those out here. We had the cosine sum identity, so the cosine of x plus y. Recall that was cosine x cosine y minus sine x times the sine of y. And the difference identity for cosine, cosine of x minus y, is equal to cosine x cosine y plus sine x sine y. And this basically, if you look at these 4 identities are very important. They're worth knowing. But you can see that the 2 identities for cosine are similar. They're only different by the sign in the middle. And the same thing is true for the sine identities. So let's recall how we've already used these identities by doing an example. Let's take a look at the sine of 75 degrees. Now, 75 degrees is not one of the angles that we have memorized the exact trig values for. So our challenge here is to figure out if there's a way to express sine of 75 degrees, if we can take that angle 75 degrees and express that in terms of angles we already know. So perhaps you've already thought about this and know that we could write this as the sine of 30 plus 45 degrees. Now we can apply the angle sum formula or identity for sine, and that would tell us that this is the sine of 30, the cosine of 45, plus the cosine of 30 times the sine of 45. And now these are exact values of trig functions we know. So the sine of 30 is 1/2. The cosine of 45 square root of 2 over 2. The cosine of 30 is the square root of 3 over 2, and the sine of 45 is the square root of 2 over 2. So we have exact values here, which means now that we're going to know exactly what the sine of 75 degrees is. We have 1/2 times the square root of 2 over 2. We can simply multiply straight across. That gives us the square root of 2 over 4. And again, we can take the second term and multiply straight across. The square root of 3 times the square root of 2 will give us the square root of 6, and 2 times 2 will give us 4. Since these are written over the same denominator of 4, we can simply add these 2 terms together, and we get the answer that the sine of 75 degrees is equal to the square root of 2 plus the square root of 6, all divided by 4. This isn't the only way we could approach this problem. Another way to come up with the angle of 75 degrees would be to take, for example, the sine of 135 degrees minus 60 degrees, and then we could apply the difference identity there. I'm not going to do this problem for you, but just to show you that there are multiple ways often of getting these angles that we're interested in. You'll notice that the problems that were assigned to you were problems involving angles expressed in degrees, not in radians. So working with angles in radians is a little bit more complicated, as you already know. But there are some ways around this, and I'm going to show you 2 different ways very briefly, so that if you have problems involving radians, you have techniques of where to go. So for example, let's suppose I'm asked to think about what the sine of 7 pi over 12 is. Pi over 12 is not a unit of angle that we have memorized the trig values for on the unit circle we have. the pi over 6, pi over 3, pi over 4, pi over 2, and multiples of those, but we do not have pi over 12. So that means that we have to think about this angle and how to build this angle out of angles we do know. One way to go through and do this is to take 7 pi over 12 and simply convert to degrees. Okay, we can turn this problem into a degree problem. Degrees are much easier to work with sum and difference, so we can take our 7 pi over 12 and we can multiply it by 360 divided by 2 pi, or 180 over pi, depending on what you'd like. Pi's cancel out, 12 goes into 360 30 times, 30 divided by 2 is 15, 15 times 7 is 105 degrees. So the equivalent problem here would be to find the sine of 105 degrees, and we can take 45 and 60, for example, and add those together to give us 105, or we could take 135 minus 30, several ways of going through and doing that. If you choose not to convert these angles into degrees, but rather work in radians, I applaud you. The problem gets a little bit more difficult. What we have to do is we have to think of 7 pi over 12 now as the sum or difference of two fractions. And the fractions have to have denominators of either 2, 3, 4, or 6, because those are the angles that we know exactly. Well, 12, there's two different ways that we could work with 12. We could be combining fractions that have denominators of 2 and 6, or we could be combining denominators of values 3 and 4. In this particular case, 7 pi over 12 is actually pi over 3 plus pi over 4. I know this because when I go to think about this, 3 and 4 form a denominator of 12, but when I actually go to get a common denominator, I'm going to be adding the 4 and the 3, and that's going to give me that 7 there. So there's not necessarily a firm and consistent way of getting the angle written out in radians. You kind of have to play around with things a little bit, and it is more complicated because it is fractions. Well, let me talk to you about another kind of problem you're going to be seeing that will get you working with multiple identities, both the sum and difference identities, but also the Pythagorean identities. So as an example here, let's suppose we're asked to find the sine of x minus y if the sine of x is 2/3 and the cosine of y is 5/7. And let's suppose, just for the sake of argument, because we don't really need to go any farther, let's suppose that the angles x and y are both in quadrant 1. Okay? Both the angles are in quadrant 1. Well, sine of x minus y, we can use the difference identity for sine to come up with the fact that this has to be the sine of x, the cosine of y, minus the cosine of x times the sine of y. And if you look at this, we actually know several of these pieces already. For example, here we have the sine of x, but we're given what the sine of x is, and the cosine of y, and we're given what the cosine of y is. So this first term is no problem. Sine of x is 2/3, cosine of y is 5/7. But the second term, we don't know what those values are. We don't know what cosine of x is. We don't know what sine of y is. So if you think about how to approach this problem, because I know the sine of x, I can actually get the cosine of x as well. We can do that calculation over here on the side. Recall that sine of x is 2/3. We would like to know what cosine of x is. We can use the Pythagorean identity. And I can say that sine squared of x plus cosine squared of x equals 1. But sine we're given is 2/3, so we have 2/3 squared plus cosine squared x will equal 1. Doing this very quickly, 2/3 squared is 4/9, so we have 4/9 plus cosine squared x equals 9/9, and I'm just going to anticipate wanting to write that 1 on the right-hand side in terms of a fraction I can use here. That tells me that the cosine squared of x will be 5/9 when I subtract the 4/9 from both sides, or that the cosine of x will equal plus or minus the square root of 5/3 when I take the square root. And of course, in this particular case, because x is an angle in quadrant 1, we know that cosine has to be positive. So I can go ahead and put in a square root of 5/3 here, for sine of, or for cosine of x. Coming back up here, we can see that cosine of y is 5/7, and if you do the work, you will find, well, let's go ahead and do that work just so that you can see that. So the cosine of y is 5/7. Cosine of y is 5/7. We would like the sine of y. So again, we can say that the sine squared of y plus the cosine squared of y has to equal 1, or that sine squared of y plus 25 over 49 is equal to 49 over 49. So the sine squared of y is equal to 24 over 49, or sine of y is equal to plus or minus the square root of 24 over 7. And again, we'll choose the positive root because we're in the first quadrant. So we have sine of y here is the square root of 24 over 7. And now we can simplify this problem by combining things together. 2 times 5 is 10. 7 times 3 rather is 21. Minus 5 times 24 is 120. So this will be minus the square root of 120 over 21. And so our answer will be 10 minus the square root of 120 over 21. That will be our answer there. So this particular problem involves making use of the Pythagorean identity as well to find missing trig functions so that we're able to solve a particular given problem. I hope this helps with the homework and that you are able to proceed through things relatively easily.